Hello, chemistry students of Block B, D, and for F as well. This is lecture number 4, given on Friday, January 29th, I think, or Monday, February 1st. So this is the last lecture for Unit 4. So let me go to the PowerPoint for this. So if you're listening on Friday, you're listening to a tape because I'm not there on Friday, January 29th, but if you're in F block, you may have heard this before. So anyway, the last time we did stuff, so far in this unit, this chapter, we have balanced chemical equations. We have looked at different types of reactions. We have looked at chemical equilibrium and rates of reactions in very general detail, answered some questions about that in homework 3. Now we're going to look at 3 different reactions in more specific detail. We're going to be able to actually predict the outcomes of these reactions. In other words, if we're given reactants, we'll be able to actually put products down put down products and figure out how the atoms are rearranging, and we'll actually be able to figure out some other things about the products as well. So the 3 reactions we're going to do are called single displacement reactions, double displacement reactions, and also combustion reactions. So let's start out with single displacement reactions. Okay, so basically they're ionic. So let me put down first, oops, see if I can get this to work here. Ionic. So usually you're going to see something that's a metal here, alkali metal, alkali earth metal, or metal. Then you're going to see a cation, which is a metal, and an anion here. And then you're going to figure out that this guy kicks out this guy. Cation former a metal. Anybody from groups 1 through 13 will kick out the other cation. So the other cation goes home as a metal, and this guy becomes ionic. So we just actually display states. So the first person in the formula goes away. It's replaced by the element that's shown here. So element, ionic compound, new ionic compound, and new element going home. Okay, so first of all, there are actually 2 types. I just gave you the cation displacement. So one of the things you have to look for in this is, first of all, know it's a single displacement. How do you see that? Well, you see singles on both sides. Here's a single, here's an element. Elements on both sides. But it's not the same element on both sides. First thing you want to figure out is whether this element on the left in the reactants, is that on the left side of the periodic table? In other words, groups or columns 1 through 13, which you've learned have positive charges. And if they are, then you expect this guy to kick out the first guy. You always write the cation first in a formula. So you can see here, zinc is a metal, kicks out another metal named copper, and it goes home with the chloride, which is the nonmetal. However, if you look at this one, if you look up bromine in the periodic table, that is not in the first, that is not in the first 13 groups. It's actually a halogen. Halogens don't form cations. So we have to look at this as it being displacing the girl, the anion. And then you can see here, K and Br go home together and the girl goes home alone. So that's one of the first things we have to do when we're given a setup. So what is the question? You're going to be given this, and you'll have to give this out. Sounds pretty easy, but you have to watch your formulas again. So let's try it. So first thing, so like I said, we're going to put the products, but when we put the products, make sure we put in the right formulas. So aluminum. Aluminum is a metal. It is in the first 13 groups. So it's going to kick out this guy, which we always write the metal first. So aluminum is going to go home with the nitrate. Now notice I didn't put 2 nitrates yet. And then the lead goes home alone. By the way, these elements, at least the cation ones, they're not, remember we have to look out for any elements that are diatomic. Those are the ones like nitrogen, oxygen, and the halogens, but we don't have to worry about that here. So next thing we have to do though, is you might say, why didn't we put a 2 here? Why didn't we put a 3 by here? Well, we have to balance it later. We have to put the right formulas in first. So as I put in many, many years of doing this, do the pattern, which we just did. do the subscripts or the formulas, remember that is not looking at what's on the left and then balance at the end. So that's what we have to do for this, and you're going to find these types of problems in your homework. So aluminum is +3. Nitrate, if you remember, is -1. So this is the right formula for aluminum nitrate. As far as lead is concerned, that is monatomic. So now we can balance it. So we have 2 aluminums versus 2 over here. Nitrates, we have 2 versus 3. Let's take care of our aluminums first. Let's put a 2 here. And when we do that, we get 6 nitrates. Guess what? We have 6 nitrates. Way to go. Now, we have to get 3 leads, though, so I'll put a 3 over here. So remember, coefficients are used to balance. There we go. Next one, magnesium is a alkali earth metal. It is in column 2, so it's definitely going to displace the first element in the ionic formula. So we're going to put Mg. Let's go ahead and put the charge in. That's +2. And it's going to go home with chlorine as an ion. That's -1. So we're going to get MgCl2. Plus, who's going home alone is hydrogen. Now, it's an element. Is it one of the diatomic elements? The answer is yes. Okay, who are the diatomic elements again? Let me go real quick. Remind you of about a week ago. We talked about a few elements they have to commit to memory that are diatomic. Sorry, let me see if I can get there. Someday I'll get there. Sorry. Couple more here. There they are. Here are your diatomic elements. So just look, whenever you put an element down in as something that's formed, just check to see if it's diatomic. So let me go all the way through back to here. Okay, here we go. Okay, so, all right. So there's H2. Okay, now let's balance it. Magnesium's okay. I always do hydrogen last, by the way. Chlorine is okay. And hydrogen's already okay, so we're good. It's partially because I balanced this on the left already. So chlorine, that's a halogen. That is not a metal, so that's going to kick out bromine. So we're going to put down that K goes home with Cl. Put in the charges, since it's ionic, it's KCl. Plus, bromine goes home, and bromine is a halogen, and as such is a diatomic element. Let's see if we have to do any balancing, and indeed we do. We have to get 2 Ks and 2 Cls, so I'll put a 2 here, and we're done. So that's how we do that one. So there's a bunch of work in your homework where you're going to do the outcomes of single replacement. Next part of your homework. This seems kind of weird. This is for cations replacing cations, or the men replacing the men. We're going to ask whether the reaction can happen. You're like, what? Well, we wrote down some that can happen and that can't happen. So the idea here is we have a list of studs of men of cations. And we're going to ask, are we on the top of the stud list, like lithium and potassium? If we are, we can kick out any of the boys below us in that reaction. So let me give you an example then. Let's use a table. Can K, all these by the way are men, can K kick out Na? Let's look. Okay, let's find K. Let's find Na. Since K, the single stud, is tougher than the boy that has the girl, he can kick out the boy that has the girl. So this one is a definite yes. Sorry, I don't know what's going on here. So let me see if I can write in here. Yes. Let's see if aluminum can kick nickel's butt. And that this reaction can happen. Can aluminum displace nickel? Let's find aluminum. Let's find nickel. Again, aluminum's above nickel. The single guy can displace the other guy, so I'll put a yes here. Can nickel displace copper? Is nickel above copper in the list? You already have nickel. Where's copper? Where is copper? And oh my goodness, I made these all work. Nickel can displace copper, so we'll put a yes there. Can zinc kick the butt of lead? Is zinc above lead? Okay, where is zinc? Zinc above lead. Yes. I wasn't very creative, but all these can work. So I'll put a big yes here too. Let me give you one that won't work then. Finally, how about Na plus KCl? Can that work? Is Na above K? Let's look. Okay, Na is below K, so that won't work. And I knew that won't work because I just reversed the one that did work. So likewise, nickel wouldn't be able to take out aluminum chloride, which by the way would look like that. So anyway, there will be some no ones. So that's another section in your homework. So you can stop here and do a couple from your homework if you like. Now we get into a little bit harder one to predict. You'll be given this, and you'll have to predict that. Here, it's kind of like you have two double dates, and they switch dates actually. So again, you have to know the pattern, you have to do the formulas, and then you have one more job. After you do the formulas, instead of asking can this happen, you're going to ask whether one of the new couples, turns out both of these guys here, we're going to say are soluble in water and they're aqueous. We're going to see whether these guys are still soluble in water, or whether it turns out that they would form a precipitate in water. What is a precipitate? In other words, let's say sodium fluoride does not dissolve in water. It will come out as a solid on the bottom of your test tube. So you would see two things that look like water, but these are dissolved in them. But then one of these, if this is insoluble, will be soluble. In fact, in your lab, you'll see this reaction actually. So yeah, we're going to finish the reaction. We're going to give the rate formulas. We're going to balance. But then we're going to ask a different question, not whether it can happen, but whether the products are soluble or not. So let's go there. So here we go. I call them precipitation reactions. They're ionic compounds in water. So they're soluble ones. A lot of ionic compounds are soluble, but some of them are not. So these two, this reactant and this reactant, are in water solution. You mix the two water solutions together. Then these ions, which are separate, turns out when you're soluble, you're really separate ions. But when barium now bumps into sulfate, oh my goodness, they stay together. And when they stay together, they actually form a solid or a precipitate. So anyway, how do we figure out if they're soluble or not? So when we make these products, which we'll practice doing, so barium now is with sulfate, magnesium is now with chloride. In fact, what we're going to do is we're just going to do like this. We're going to take A and flip it for C to make our products. That's what we're going to do. But anyway, let's say we did that. We're going to look up barium sulfate and magnesium chloride. But it turns out we're not going to look it up to see if it's soluble. We're going to look up what class it's in. So what does it mean by this? Most of the time we're going to look at it and say, it's a sulfate. This one's a chloride. Are these generally soluble or insoluble? We have a table for that. So instead of looking at barium sulfate, we're going to look up at sulfates and see if they're soluble, and chlorides. We're always looking at the anion most of the time. So let's look up barium sulfate on the next table. So this table says one thing, this table says another. This table's giving you all the people who date a woman who make them soluble in water. So ions that form soluble. Notice there is a couple men on here. If you have a cation of this, no matter who the girl is, no matter who the anion is, you're soluble. Almost all the rest of these are about the girl. The girl has a lot more to do. The anion has a lot more to do with whether you're soluble. So let's look up at sulfate. Barium sulfate. Sulfates are normally soluble. We just said it was insoluble and a precipitate. But then we look at the exceptions. There it is, barium. So barium makes it insoluble. Let's look up the other one. Magnesium chloride. So we're going to look up chloride. Here it is, right here. Chlorides normally are soluble. There's some exceptions if you're with these three men. These three cations are not, but magnesium's not one of them. So magnesium chloride is soluble. Now before you panic and say, well, I have to memorize this table to figure out if they're soluble or insoluble? No, you don't. You just have to know how to use it. Now, one morning, when you look at these other anions, these are generally form insoluble. That means they're precipitates or solids in water. But there's exceptions that make them soluble. So you have to reverse your thinking on this table. So best thing to do is to practice this again. Okay, so let me put the steps down. Do the pattern, swap the partners, do the swap. Number 2, formulas. It's charges and crossovers. They're not the same as on the other side. Balance the reaction, which you now know how to do pretty well. And then look for solubility using the table, which you get to use for the test and the quizzes. So here's the pattern first. Silver, which by the way is a +1. You can look that up. You can always look these up still. And then you have carbonate, which is -2. So this is Ag2CO3. Why? Because you put the charges in. This is what you did all of last chapter. Now lithium now, so you just went backwards. Lithium is now with nitrate. Lithium is +1 and nitrate is -1. So we got that. Okay, let's balance it. Well, my silvers are off, so I need to put a 2 here. I'm doing this by eye, by the way. We could write this on the board if you like. So we got 2 silvers. Now I got 2 nitrates, so I better put a 2 here now. When I do that, my lithiums are good, and now my carbonate's good. So anyway, if you need to stop and balance this on the board, that's great. But just know that you need to balance it next by counting your silvers, carbonates, nitrates, and lithiums. Okay, now, next thing we're going to do, let's look up some of these guys. So are they soluble or aqueous? So by the way, we're going to assume that these guys were aqueous. But now we want to know whether our products are aqueous. Are they soluble or insoluble? If they're soluble, they're aqueous. If they're insoluble, they're solid. Let's look up carbonate first. Okay, where is carbonate on this thing? Here it is. Carbonates are generally insoluble. It says ions that form insoluble. Unless they're with group 1. What is group 1? That's the first column in the periodic table, your alkali metals. So let's see what carbonate's with. Okay, carbonate is with silver. So this is actually a solid. So this is not aqueous anymore. It comes out as a snot. What about lithium nitrate? We can look up nitrate. There's nitrate right here. It says it's under the column that says soluble, and there's no exceptions. In fact, lithium's on here too, and it's always soluble. So you don't need to look up both of them though, but they both are internally agree. So this one is aqueous. And now you've done what you do in the homework and what you're going to do in the quiz. Try the next one. Swap your men. So barium is now with phosphite. And sodium is now with chlorate. Okay, did the partner swap? A lot of people do this. They go barium, phosphite, sodium, chlorate. Please put your cations first, the men first, and the women second. That'll make it a lot easier. Look up your charges, do your formulas second. So you swap them, you get Ba3, PO3, 2, +1, -1, so 1, 1. Okay, let's balance this sucker. Barium's way off, so I'll put a 3 here. Okay, phosphite needs a 2. Sodium, oh wow, I got a lot of stuff screwed up. And by the way, I also gave you the wrong information. There should have been a 2 there. So I have 3 bariums, that's good. 2 phosphates, that's good. But now I have 6 sodiums and I have 6 chlorites. So I need to put a 6 here. Okay, cool. Sorry about giving you the wrong information on the reactant side. Let's look up phosphates and chlorites. Now I made a mistake on this for a second time. Phosphates have the same rule as phosphates, so I won't put one line on the quiz like this because you wouldn't find phosphate. Let's assume it's insoluble. So all phosphates are insoluble, and that's where they're with group 1. This is a group 2, so we'll put solid here. Let's look up chlorites. Again, to figure out soluble, look at the woman. Are people with chlorite soluble? Okay, where's chlorite? There it is. Chlorate, I should say. It's soluble. No exceptions. So we'll put aqueous for that one. Okay, let's do the next swap. Calcium and magnesium. Calcium goes home with sulfate. Magnesium goes home with hydroxide. Now we'll do the formulas. +2, -2. That's 2, 2, but let's just put 1, 1. Magnesium's +2, hydroxide's -1, so that's MgOH2. And you know what? It's balanced. OH2, Mg1, everything's balanced, so that's great. So we're now ready to do looking at the solubility. So let's look up sulfate first. Sulfate is soluble, and that's what those dudes. It's with magnesium, so it's still soluble. I'm sorry, calcium is with calcium. Sorry, let me look at calcium again. Oh, bingo. It is not soluble. So we're going to put a big S here. What about magnesium hydroxide? Hydroxide's insoluble, and that's with group 1, or with those guys. Who's it with again? Oops, sorry. Trying to get this to go. It is with magnesium. Guess what? Let me look back again. Nope, it is insoluble. We got 2 big precipitates coming out. These are both solids. Cool. All right, so you got the idea. So the big thing with these problems, people have struggled with them before, mainly because they don't look at them as 4 steps. They're not strict enough and have enough patience, and I don't mean this in a bad way. I'm just telling you what to do when you do these on your homework. Don't try to do everything at once. You can't. You got to do the pattern swap. You got to get the right formulas. If the formulas are wrong, you won't be able to balance it. If you don't get the right swap, you won't be able to do anything either. So to do each step, you have to do the previous step correctly and separately than the previous step. So you got to get the right formulas, otherwise it won't balance. So if you can't get it to balance, go back to the previous step. And number 4 is independent, but you have to at least do the swap right to do number 4. So these 2 things are where people really struggle. Step 2 and 3. Do your formulas, look up your charges. You can have all that material with you, but make sure those are right before you balance. Combustion reactions are the last thing. Not much to say about them except you put in some type of a CH compound, and the recipe is this. You add oxygen, and you always produce CO2 and water. What's different from one to the other? The balancing. That's all it is. So all we have to do is practice this. So this will be the way it would be on your quiz and homework. So first of all, you have to know the pattern. It's always plus O2, CO2, and water. So let me put that pattern in for all of these. Plus O2 gives you CO2 and water. This one gives O2 plus CO2 and water. Okay, remember to balance, you do C, H, and O. So on this one, we got 3 versus 1. We got 8 versus 2. And of course, we got 2 versus 3. Let me show you the 2 versus 3. 2, and then there's 3. So watch it. Watch your oxygens very carefully. So balance your C, you do this. And now you got 7 oxygens. So I got rid of my C there. But putting a 3 in front of the C gives me 6 plus 1 is that. Let me put a 4 here to get my hydrogens to 8. And now I have 6, 10. Yep, 4 plus 6 is 10. Now balance my oxygens. I can put a 5 in front of the oxygen. So far so good. Let's try CH4 one. CHO. Make your little diagram here. 1C, 1C. Very good. 4 H's, 2 H's. 2 oxygens, 3. It always comes out as 2 versus 3 no matter what for oxygen. So we need to do the hydrogen for sure, but not the carbon. So whoops, my bad. Let's put a 2 there. So if I put a 2 there, I get a 4. And now I have 4 oxygens, so I just put a 2 here and I'm all set. Not bad. Let's try the next one. CHNO. 7 carbons in 1, 14 hydrogens in 2, and 2 versus 3. So I'll put a 7 here to get my carbons correct. Now I got 14, 15 oxygens after that. Now I'm going to do my hydrogens. I got 14 now because I put a 7 in front of that one. My total oxygens are 14 plus 7 is 21. Now you're going to freak out. You're like, I have to go from 2 to 21 oxygens. And I can only put it over here. So go for it. You can't put in a whole number there. 2 times 10 equals 20. 2 times 11 equals 22. Let's go for the least common multiple of 42. Okay, let's do that then. To make your oxygens on this side double, you're going to have to double these 2 coefficients, both of them. I'll put a 14 and a 14. So now I have 28, 42 for here, which means I'll put a 21 over here. And I might say, well, I really did some bad things here. Look at this. I got 14 carbons now, and I got 28 hydrogens because of what I did. But all you have to do is go to this side and put a 2 here, and you're all set. So that is it for the lectures. We will have a lab when I see you on Tuesday next week. And then we'll have our test on Thursday. And yeah, or it might be Wednesday. Oh, I'm sorry, I'll figure out what. Yes, it is Thursday. I'm thinking about the next week where I have Monday off. So anyway, I'll see you on Tuesday, where we'll have a lab and a quiz on homeworks 3 and 4. Thank you.